In this section, I'm going to be talking about the concept of a probability continuity equation. um, and so this is actually a really interesting topic because we go a little bit more into the mathematics, and we are going to produce actually a quite elegant solution of how the probability changes with respect to time. Or basically, if we want to consider how the probability is conserved over time. And so a good example of a conservation law is the electric charge. So globally, charge is conserved. So, if we're to consider all of the charge in the universe, that charge should actually be neutral because it started with the Big Bang. But I mean, if we add up all of the charge, then it should be equal to the same amount of charge we had 10 minutes ago and the same amount of charge we had a year ago. So globally, charge is a quantity that we understand to be conserved. Locally, we can move charge around. So we can move charge from one place to another. Okay, so in that case, what we have to take into account is the flow of the charge. How are we relating? How are we relating how the charge is moving from one location to the next? So the connection to that is the electric current, and so we have this equation that the time derivative of the charge density, so rho is a charge density, and that's equal to the divergence of the electric current. So you've probably seen this in your classes on electricity and magnetism. You've probably seen this continuity equation that if we're going to change the charge over time, that has to be related to how that charge flows out of the system. So if we consider this charge density, we had a bunch of charges in space, and then we move those charges basically by a current. So we have this current J, which is the motion of the charge. We can basically calculate the charge inside this volume with this equation. So if we integrate over the charge density with respect to space, basically over this three-dimensional volume, and how that changes with time, should be equal to the integration over the volume of the divergence of the current, which, if we use the divergence theorem, says it is the integral over the surface area, the enclosed surface area of this volume, the current dotted into that surface area. So again, there's a continuity. If we have a certain amount of charge and we encapsulate it in this kind of Gaussian surface, then any charge that leaves that has to be taken into account. We should be able to account for the divergence of the charge out of the Gaussian surface. And that's related to how the density of the charge density, the charge over the volume, changes with respect to time. So that's kind of an example of the continuity equation for electric charge. Now what I'd like to do is to apply it to quantum mechanics. So instead of the quantity that's being conserved being charge, we want to look at the quantity of the probability. So if I start with a probability, basically I have some state psi with respect to time. I can get that state from the initial time t equals 0 by using the propagator. So u dagger, which is time dependent, and then u, which is time dependent, with psi at time t equals 0. So u is unitary, and so u dagger u is just the identity. And since u dagger u is the identity, then what I should have is the probability at t equals 0. So the probability in the initial time, t equals 0, should be equal to the probability at any other time, t. The probability should be conserved. Or another way of saying it, this overall probability is a constant. Okay, so now let's approach this like we did with the charge density, and let's integrate over the probability, well, the probability density. So this is our probability density. Let's integrate over all space. So so I'm going to project this into an XYZ volume and then integrate it over all space. So we basically have psi of t in x, y, z. So we've projected it onto a Cartesian basis. And then the other one would be x, y, z projected onto the ket. And then we integrate that over dx, dy, dz. We could probably shorten this a little bit so we can keep it on the page as the three-dimensional integral of psi with the basis r integrated over the three-dimensional volume d3. So these are nothing more than the wave functions with respect to position and time. And so now I can write this down as the triple integral of the probability density integrated over the volume, like so. So if I write this down now as the integral of the probability density with respect to position and time integrated over all space. So now we have a function, probability density, which is going to be sitting in for our charge density. Okay, so that's the left-hand side. We can take the derivative with respect to time on that, like we did to get the continuity equation. But let's try and figure out what the current is. How can we calculate the current of our probability? How is our probability flowing out of a Gaussian surface, spreading out over the space in a certain period of time? Well, to do that, we're going to start with the Schrodinger equation. So our Schrodinger equation so I'm going to write this over three-dimensional space. So the partial derivatives with respect to position are now the del, in this case del squared, plus any kind of potential right here. So we've got, the energy operator and the Hamiltonian operator. So we've written out the Schrodinger equation. And now what I want to do is let's write out the Schrodinger equation for the complex conjugate. So if we take the complex conjugate of this, we get minus I h bar, and then the complex conjugate of the wave function. So the kinetic energy term is real. So the only thing we change is the complex conjugate of the wave function. Plus, if we assume that the potential is a real function, that's just v, and then we take the complex conjugate of the wave function. So we're assuming v is real. Okay, so now let's take our two Schrodinger equations, one for the psi and one for psi star, and we'll take the second one and we will subtract the second one. So equation 2, we'll subtract it from equation 1. So if that's the case, this minus sign in equation 2 becomes positive. So I have I h bar, oh, I'm sorry, I skipped a step. First, let's multiply equation 1 by psi star. So we get I h bar psi star d psi dt is equal to minus h bar squared over 2m psi star del squared psi plus v psi star psi. And then let's multiply equation 2 by psi. So we have minus I h bar psi derivative of psi star dt minus h bar squared over 2m psi del squared psi star plus v psi star. Okay, so psi star psi is the same thing as psi star. So it's still the same probability density. So now what we're going to do is we're going to take equation 4 and subtract it from equation 3. So that gives us now I h bar, the quantity psi star d psi dt plus psi, the derivative of psi star dt, so that's the left-hand side, is equal to minus h bar squared over 2m psi star del squared psi minus, because remember we're subtracting 4 from 3, psi del squared psi star. And then if we look up here, the potential terms are identical, so if we subtract them we get 0. Okay. So the potential drops out in this exercise. Okay. So now what we're going to do is we're going to clean things up. And so with this first term, with the time-dependent derivative, that's just the chain rule. So that becomes I h bar d of psi star psi with respect to time. And with the second term, that becomes a little bit more complicated. So let's just write the term out, and we'll deal with that in a minute. Okay, so let's stop here at this point in this video, and in the next video I'll reduce this even further and then make the connection between probability density and the probability density current.